Welcome. We are Team 22 and have been tasked by EGB320 to develop a TRL-3 prototype lunar rover. Today we will demonstrate the sample collection rover and how it performed in the constrained simulated lunar scenario. We will present concepts and capabilities of our rover for greater funding by the ASA and grow Australia's potential in space exploration and habitation. The rover will be able to collect regular samples, represented as orange golf balls, and return them to the lander for chemical composition analysis.
Specification and constraints of the challenge is that the robot must be able to fit within a 150mm cube when starting on the lander. The robot must be able to detect rocks as well as obstacles while also avoiding them. This must be done within 5 minutes after the robot activates. For mobility, the team went with a track design that was 150mm in width with an 18mm gap between the bottom and the floor to prevent the robot from falling over or bottoming out on the lander. The robot turns by rotating each motor in opposite direction, allowing it to turn in tight spaces. We used two 120:1 plastic gear motors to give the robot a maximum speed of 200mm per second and a minimum of 50mm per second. A buck converter that outputs 5 volts from an input of 7.4 was used to power the motors, motor controller, and Raspberry Pi. The motor controller takes 2 inputs from the Pi per motor to control the direction and speed of each motor. To indicate the task, 3 LEDs were used. A red one that shows the robot is searching for a sample, a green one that shows the robot is returning to the lander, and a yellow one that shows the robot is attempting to collect a sample. The robot uses a proportional controller to adjust the speed of the individual motors based on the input angle.
As you can see, the sample collector is a scooping mechanism designed precisely around the shape of the sample. It has been designed in Fusion 360, then 3D printed for the prototype. When the rover is at the position of the sample, a servo motor rotates, giving tension to a line and rotating the scoop around a fixed point. It can collect a sample in open field and when it is sitting against a solid object. It has 2 prongs at the front, which is used to flip rocks revealing a sample underneath and can accurately place the sample back into the lander. To control the servo, the PWM is changed dynamically based on the angle the servo needs to sit at.
To allow the rover to interpret the environment and to identify samples, rocks, obstacles, landers, and walls, the design is attached with a camera, allowing it to see the environment. But how does the design actually interpret what it sees? To do this, we use OpenCV2 in Python. We call a frame to get an image of the camera input, then reduce the resolution to reduce the necessary computation and convert the image to HSV, as identifying color regions are easier using the Q value. We are now ready to begin identifying regions. Using the in-range command with the frame, we can identify the environmental objects defined by the range of each object. We can then erode and dilate to remove any anomalies, returning a clean mask. We can then use the Fine Contours command to depict the shapes and sizes of all the objects. The contour bodies are turned into a rover object class, depicting all necessary information for the integrated system, such as bearing and distance of objects.
Due to the limited budget and size requirements, it was decided that a reactive path planning technique would be chosen, which was potential fields. We made a modular code that could take any object as the goal and would determine the obstacles based on the goal. This code, which is displayed now, would create an attractive force and repulsive force, and this would be combined, and the highest point in this new array would be the direction angle. Before everything was calculated, the list of obstacles were filtered to remove obstacles further than the goal. In the image shown now, it shows the goal with an obstacle in the way, showing the resulting array. All of our individual designs integrated together to get the final product. The vision system would create an object that contained the data of all visible objects. This information would then go through the navigational code, which would produce a directional angle. This directional angle was then sent to the mobility's P controller to travel towards the goal. And once the goal was at a desired distance, the sample collector would activate. The integrated system would behave differently for the different goals, all while avoiding the rest of the objects. For collecting samples in the open, it would use navigation to head to the sample, and once it detected it would collide with an obstacle, it would swing out and continue for the sample. And once close enough, it would travel a set distance and collect the sample. When a rock was the goal, instead of collecting a sample, it would flip the rock and check for samples. If an obstacle was the goal, it would travel to one of the corners and once close would travel around the obstacle, stopping once near a wall, and would check for samples. If the lander was the goal and the robot was too close, it would turn both sides and find the middle of the lander, then stop at the top. For the full demonstration, it would start by collecting all in open samples, stopping once the timer went off, signaling a full rotation. Next, it would go to each obstacle, checking behind them for balls, stopping once 3 were searched or 2 samples in total were collected. Finally, the rover would flip the rocks and return with the samples. Once the desired amount of samples were collected, it would shut down on top of the lander. This concludes the video.